just now we have this one. I lost you, excuse me, and it is very interesting theme for us, of course, and I wondered why we haven't listened today. It's my fault, excuse me, and your talk had to be before Julia. Okay, now we are listening.
Hello, Chairman.
Okay.
Hello, everybody.
Excuse me once more. You are welcome.
So first of all, I would like to thank the members of the organizing committee for offering us the chance to participate to this international conference. I'm Mrs. Soumia Saïdi from Laboratory of Pure and Applied Mathematics, Mohamed Sadiq Ben Yahya University of Jijel from Algeria. It's a pleasure to me to contribute to your conference with an oral talk entitled On a Problem Governed by Subdifferentials and Caputo Fractional Derivatives. Let's start with a brief introduction. So differential equations of fractional order have recently proved valuable tools in modeling many phenomena in different fields of science and engineering. There are several applications to problems in viscoelasticity, electrochemistry, control, porous media, electromagnetics, etc. There has been a significant theoretical development in fractional differential equations in recent years. More recently, considerable attention has been given to the existence of solutions of boundary value problems with caputo fractional derivatives. The aim of the present work is to connect differential inclusions with caputo fractional derivatives in the context of finite dimensional setting. In all that comes, we use the following notation: I for an interval of R, H for a Hilbert space, BH the closed unit ball of H, C, IH the space of continuous function from an interval to the Hilbert space H, L2 the space of square integrable functions, the domain, the effective domain of a real valued function, phi star the conjugate function of a real valued function, and the subdifferential is denoted as follows. We need to recall an existence and uniqueness result. So if we consider a time and state dependent function that is proper, lower, semi-continuous and convex in state, and such that there exist two functions. The first one is Lipschitz. The second one is absolutely continuous with derivative in L2. And we have this estimate that involves the functional conjugate function and the two functions K and A. Under this assumption, if we consider a square integrable function, in Peralba's thesis, 1973, for any initial condition in the domain of the function at 0, the problem governed by the subdifferential of a time-dependent function with a perturbation h and initial condition has a unique absolutely continuous solution x. In 2013, by Saïdi Soumia, more developments on this problem have obtained, and an estimate in L2 of the velocity has been obtained, where sigma and eta are non-negative real constants. We recall some needed results in fractional calculus. So for a constant in the interval 1, 2, for an integrable function f, we recall the fractional Bochner integral of order gamma of the function f defined by this formula for each c in the interval 0t. And we recall also the definition of the caputo fractional derivative of order gamma of a function h, denoted CD gamma h, and defined by this expression, where n is the integer part of gamma. Also, we denote by C1H the set of functions U defined from 0t to h, whose derivatives are continuous. Of course, U is continuous. And we define this space W alpha infinity that contains the functions U in C1H, such that the caputo fractional derivatives of order alpha minus 1 is continuous, and the caputo derivative of order alpha of U is in L infinity. Now we move to a crucial lemma that plays an important role in our developments. For a function which is in L infinity and an element x in H, the function U is in W alpha infinity, or in is a solution, is a W alpha infinity solution to the fractional derivative equation with an initial condition U0 equals x, if and only if ut is expressed as follows. And we have this expression that involves the element, the initial condition, and this term is the Buchner integral of f of order alpha. Now we move to our main existence result. The theorem was recently proved by Saïdi. The paper was published in the Journal of Nonlinear and Rational Analysis 2021. If we are placed in a Hilbert space of finite dimensional setting, if we consider a real valued function that satisfies H1, H2, let f be a bounded continuous function. Then for an initial condition U0 x0 that belongs to the domain of phi at 0 and such that x0 in H, there is an absolutely continuous map U and a W alpha infinity map X, such that we have this coupled system involving a differential inclusion by the subdifferential of a time-dependent function, plus a perturbation which is single valued, and a differential equation with caputo fraction derivative, and of course the initial conditions. So we are going to investigate the existence of such functions. For the proof of our theorem, we are going to use the previous proposition we called above, using the assumption on F. For any bounded continuous H, there is a unique absolutely continuous solution to this problem by the existence and uniqueness result, such that the velocity of the solution is square integrable in view of the estimate obtained and recalled above, so that we can find a constant L that verifies this estimate. Now we define the closed convex subset in the Banach space C0TH by the functions defined by this formula for energy in the set of all integrable selections of the convex compact set valued constant map. We are going to use a fixed point theorem. For this purpose, we define a function t from x, and clearly it takes values from x, and prove that the images of the set x is are relatively compact sets. So for this purpose, we observe that as CHT belongs to this set, and the convex compact valued map that associates CLBH, which is the closed unit ball, is integrably bounded. The second member is convex compact valued, so that X is continuous and relatively compact in the Banach space by Ascoli theorem. Now we move to verify the continuity of the map C. Let's go using the sequentially continuity. If we take a sequence H and that uniformly converges to H in the closed set X, then we are going to prove that the associated solution VHN converges uniformly to the absolutely continuous solution VH associated to the first order problem governed by the subdifferential with the single valued perturbation. And since F is bounded continuous along with the pointwise convergence of Hn to H, we easily find or conclude these limits using the dominated convergence theorem. And we deduce the weak convergence of the perturbation in L2. Then invoking the closure property of the subdifferential, we deduce the required inclusion. So that's by uniqueness, U equals VH. Now we come back to the function, to the definition of psi, and some computations yield the required conversions. That is, VHN converges to VH, and as a consequence, PSIHN converges to PSIN, and so that we just prove the sequentially continuity of the function psi. So we have just defined a function psi from the closed convex set X in the Banach space to itself, which is continuous, such that Px is relatively compact. Then Psi has a fixed point, that is, H is expressed as follows, with the following inclusion. Coming back to Lemma and applying the above notation, this means that we have find a map H in the set W alpha infinity, satisfying the inclusion with caputo fractional derivative. And this is the proof of our main theorem. We move to a particular case of the sweeping process as a corollary. If we consider a set valued map that takes non-empty convex compact values and that varies in an absolutely continuous way in the sense of the Hausdorff distance. So if there exists an absolutely continuous map A with non-negative derivative in L2 such that we have this estimate. If we consider a single valued map which is bounded continuous, then for any initial conditions there exists an absolutely continuous map U and W alpha infinity X satisfying the sweeping process, the perturbed sweeping process, or the system coupled by the sweeping process and the caputo fractional derivative as it is written. We end our presentation by this future research as follows. So many investigations on coupled problems by differential inclusions and differential equations with caputo with fractional derivatives such as Riemann, UV, caputo, Adamar need further developments and may be the subject of forthcoming works. It is also interesting to apply this result to optimal control theory and to relaxation using Filipov's theorems. We have used the following references. The first one is recently published in 2019, involving some results on time-dependent subdifferential with applications. The second one is Peralba's thesis. And the third one is that contains a part of this presentation published recently in Journal of Nonlinear and Rational Analysis. For some applications or systems coupled by differential inclusions and caputo fractional derivative, we cite these references, which are very important. The first one contains some applications in control, while the second one involves the subdifferential with fractional differential equations. And for more details on the theory and applications of fractional differential equations, we see the two references by Kilbastri Vistava, and the readers are interested in fractional differential equations could be referred to these books. And we thank you very much for your kind attention. Thank you.
Okay, thank you very, very much. And it's very interesting that you know the results, for example, of Kilbas. And do you know results of Professor Svatya Stanek from Olomouc, Czech Republic? He also obtained results connected with caputo derivative with differential equations, and maybe it will be interesting for you to read this result, but there is no close connection between you and his results, of course. So it's only a remark. Okay, maybe somebody has questions. In Zoom, as I can see, there is no question at all, but maybe somebody would like to ask something. No, in our auditorium also we have no question, but it was very interesting and fruitful talk for everybody. For example, my student listened to your talk carefully, and I think that he can mention that your results exist. And thank you very much for your participation in our conference. Thank you once more for everybody. And I will repeat that tomorrow we will have the last today's report of our section Seshadev Pathe at 11:10, and we will have also some changing in our afternoon section, so follow schedule at our website, and we will have the closing ceremony at 7:00 p.m. tomorrow after all our talks, and the link will be the link of our section, so we will have no duty to change this line. We will remain at our section, and after other participants join this section at 7:00 p.m. So thank you very much. See you tomorrow. Wait a moment. I'll check our schedule for tomorrow morning. We will have, yes, the talk of Gennady Demidenko from Novosibirsk, Russia. After that, we will have the talk of Albert Morozov and Konstantin Morozov from Nizhny Novgorod, Russia. And after that, the talk of Sbotin and Krupenikov. It is South Ural University. And after that, the talk of Seshadev Pathya. And then we will have some change because the talk of Elena Shipakina will be at the end of our section. She is ill, and so we'll change this schedule according to this fact. Okay, thank you very much, very much. I thank all participants. It was very nice to meet you in our section again, and so see you tomorrow.
See you.
Bye.
Thank you very much.